In this video, we'll be getting started with the Arduino Uno Rev 3. This will also apply to any clones and even some of the compatibles. All right, let's start by taking a look at the Arduino Uno Rev 3. So this is the top. You'll notice the silk screen, that's the labels, pretty well marked. The clones can do this too. It kind of varies. Got our digital pins on the top, which we'll be talking about, and then some of the analog on the bottom right, and then some of the power pins. You've got your USB connector, you've got your reset, and you've got your barrel jack, and you've got your ICSP header over here as well. Here's the underboard. There's not really anything to look at. And here's the surface mount version. Most likely you probably don't have this, but just in case you do and you see it's different than the surface mount one, don't panic. And here's a Elegoo clone, pretty much the same markings and whatnot. This one actually points out a number of things. Here's the all-important pinout for the R3. Um, Now, what's labeled in yellow is the actual pins on this chip here, and then the cyan color indicates their numbering on the board. So if 13, 13, 12, and so on. If it has a little tilde symbol next to it, it means it's capable of PWM. Um, a lot of these also have secondary functions. For example, this is SPI over here. If there's a little check mark, then again, pulse width modulation. You got a few other things. Doesn't have, oh no, it does. The I2C bus over here is labeled. As I pointed out, it's powered by a USB Type B connector, which is very common on printers and scanners. It has a DC power barrel jack that can take anywhere from 7 to 12 volts. Um, a lot of kits will actually come with some kind of AC adapter, perhaps a battery holder or something for that jack. It may or may not actually come with the USB cable, and in some cases they may give you a really short one, but you probably already have one on hand. If not, you just buy one. Um, USB connection, for the most part, is going to be what you need to interface through the serial to USB for uploading code, reading, writing to the serial monitor plotter, and for some possible debugging. There are some more advanced features where you can actually program the MCU directly, but that's going to be in a much later video. You'll need a computer, tablet, smartphone with all the proper programs and connections. Um, I don't necessarily recommend doing this on a phone because on a touch keyboard, programming is very slow. But if you have to, I would invest in like a USB keyboard that's easier to type on. You'll see 4 LED on the board, which indicates power, sending data, receiving data, and a built-in LED. 0 is always tied to send, 1 is always tied to receive, and usually 13 is tied to built-in LED. If you're compiling with a compatible, sometimes it will set that to the proper one, and sometimes it won't. You'll need some kind of IDE where you can code your sketches, which is just Arduino speak for programs, upload them, and then also possibly read write to the serial. It is possible to split these functions up, though, to various programs. Now, I mentioned the term IDE. What that means is Integrated Development Environment. Prior to their emergence, you often had to write code on a simple text editor. You separately ran compilers and linkers on a command line, and then you uploaded the program with yet another tool. And then you had separate debugging tools, assuming they were even available. What an IDE is, it provides a very specialized text editor, usually has syntax highlighting, code completion, suggestions. So basically, it kind of helps you do the job in the same way that you can get a text editor that has a automatic spell checker. For example, it usually handles the checking, compiling interpretation, linking, uploading, building in one solid single package with a single front end. Keep in mind on the back end, it still might be multiple programs, but you're not going to run into that unless you really look. It often has debugging tools, at the very least software-based ones, but sometimes hardware-based ones as well, assuming your board supports it. If used with physical hardware, it might also include tools to actively monitor the device, as well as input-output, such as a serial monitor. Some of them can be incredibly complicated. Basically, they need features to support anything and everything for a given device or programming language. Then there's the official Arduino IDEs. There's some legacy 1 point, essentially O versions, the mainline 2 point, and the Arduino App Lab program that's built specifically for the Arduino Uno Q. The original Arduino IDE is Java based, and it's the only version that I think that works with Windows XP, Vista 7, 8, 32-bit Windows, 32-bit Linux, and ARM Linux. Arduino 2, that's Electron based, but that only works with Windows 10, 11, 64-bit, Mac OS 10.15 plus, 64-bit Linux, and some limited support for Chrome OS. Arduino App Lab, that's browser based, so it can run on a lot more devices, even mobile devices and tablets, but it otherwise requires Windows 10, Mac OS 10.15 plus, generally works with Linux and Chrome, iOS 16, and Android 8, but I can't think of any models that it's necessary for except for the Q. And then you have the Arduino Command Line Interpreter, or CLI. This program basically works as a backend for the other ones, but it can just be used directly on the command line for Windows, Mac OS, and Linux. There's a lot less restraints on what platforms and platform versions it works on, because again, this is just a command line program. But there's some pretty good unofficial options as well. This is helpful if you're already using them and you're already used to them. Visual Code Studio with Platform IO, Eclipse IDE, and this is a great IDE for programming in general. Visual Studio, MATLAB X, but it only does AVR based Arduinos. Chip Microchip Studio, it used to be called Atmel Studio, but again, only AVR based Arduinos. ArduBlock, which works with block coding, but it's very, very limited. If you're not learning program with block coding, just ignore that. Walkway, although you will have to do the uploading separately, obviously, or you can just break out a text editor. Of course, you'll need things to compile, upload, etc. That's where you use the Arduino CLI. Now, you're going to want to get the IDE ready. First, you got to download and install the IDE. The official one should download all the important stuff and install the drivers as needed. You might need to restart your computer. Plug in your R3 with a USB-A to USB cable. I mean, if you're connecting like your phone, you got USB-C to USB, the kit may come with one, and it may even be really short. If it does, this does have to be a cable with a data line. Power only or power delivery cables won't work, although they will still provide power. Open the IDE, see if everything's detected by the IDE. If you've got an official Arduino model or clone, it probably should immediately recognize it. It's possible the IDE has to download some libraries first, and usually you'll see a virtual COM port, COM1, 6, or 11, whatever. You may have to configure everything by hand yourself. This is very unlikely for mainline Arduino models and their clones, like the Uno Rev 3. Look for settings, preferences, set the text, the background theme to your liking. If it's going to be something that you can't stare at for like half an hour to an hour, then change things. Make it as comfortable as you can for yourself. Sort of familiarize yourself with the different main areas of the IDE. The editor, which is right in the middle. There's some buttons for verify, compile, and upload. Verify is just going to check your program, make sure it's valid. and then compile is going to put it into machine code, and then upload directly to the connected board. Mind you, there's some advanced options for compiling into hex and bin files and to do whatever with those. You'll see some board selector menus. There's a lot of details, but you shouldn't have to think much about it with the Uno Rev 3 connected to the serial over USB. You got serial monitor, you got board and library manager, you got a search bar, and then that can help a lot. Um, Start out by uploading an incredible simple sketch, the initial blink, for example, and then see if it properly compiles and uploads to the device. Don't worry if the program doesn't work. Otherwise, all you're doing is testing out the compiling and uploading at this point. Now, you might get confused with the word serial, USB. You probably know what USB means, but the combination of the two. If you didn't use computers in the 1980s or 1990s, you're probably unfamiliar with serial communication or serial ports. They largely disappeared in personal computers by the 2000s as they were replaced with USB 1/1.1 and eventually 2. It's basically the simplest form of communication between devices. Very simple signals sent back and forth. Why the USB is very, very complex because it has to establish a relationship between the two devices. It's more akin to a network. The Atmega 16U chip on the Uno Rev 3, it might be something different on some clones. Basically, converts serial data from the microcontroller to USB and back and forth. So as far as the computer or whatever you're concerned, it's dealing with USB. The microcontroller thinks it's dealing with serial. The connected device appears as a virtual serial communications port, shortened to a COM port on your computer. It fixes serial connection, as I said. You'll need a USB cable that has a data line. You can't just use one for power delivery or charging. This can be really hard to determine if it's in a mess of cables, so you might want to pull out a couple and see what happens. Sometimes computers just don't see the right device or they don't set up the virtual port correctly. Just keep trying, pull out the cable, plug it back in. Um, you're not gonna probably not gonna damage anything by doing that repeatedly. Try different cables, whatever, until it actually detects it. Now, you might have been confused when you heard the term serial monitor. Well, I just described serial. Basically, it's a way for the microcontroller to send and receive serial data so it can output messages. It can take an input from like a keyboard, although you have to set all of this up in a sketch. Many IDEs, including the official ones, they have some kind of built-in serial monitor, but you can always be old-fashioned and use a program to connect directly with that COM port and use that instead. In some cases, this actually might be more desirable because the built-in serial monitor is pretty bare bones. Um, this is pretty similar to the Telnet SSH experience if you're familiar. Otherwise, this can be incredibly confusing. The key two bits of information you need are the COM port and the baud rate for the connection to work correctly. There are other settings, but they will probably just be the default. If you want to try all that out, though, there's a program called Putty. It's free. It's been around, I really don't know how long. It's available for pretty much everything 32-bit, 64-bit ARM, Linux, Mac OS. It even works on Apple's Silicon, BSDD, React OS, but it's not available for mobile devices. The device or compiler may also communicate messages via serial monitor. So if something shows up, even when it's not part of the sketch, don't worry, that's completely normal behavior. Some of the clones and certainly the compatibles will send you a lot more information, like when it's preparing to download the sketch, when the download is happening, other useful information. Um, and errors might show up during uploading, but good news, that'll probably give you some useful information to what's going on. Now here is the Arduino 2 IDE, and I just have up the template at the moment. Ignore the board selector, I don't have anything plugged in. Now I've just plugged in an Arduino Uno in, so I bring this down and it'll say Arduino Uno, and it's already been assigned a virtual COM port, COM3. All right. Let's I don't know, let's do something to Well, actually, I've already shown blink sketches, so that doesn't really matter. But let's check out the serial monitor and how that may work. So we're going to begin at 9600. We've established our connection. Well, let's make it do something. For what? Let's say serial print line. We'll say this is the serial monitor. We only want to do it once. We would do it at top. And let's delay, I don't know, 1,000 milliseconds, make it a second. All right, we're going to verify. Oh, wait, empty character constants. There's some issue here. Oh, wait a minute. Okay. See, it'll actually give us the errors, and sometimes these errors are helpful. Okay, let's compile. Oh, no, there's still a problem here. What's the problem? Oh, okay. Hit the wrong button. Yeah, let's do this again. Nope, there's still a problem. Oh, yeah, it's weird. Why is it saying that? That's odd. Okay, well, let's retype that. All right, this time it's compiled correctly. It says how much memory it'll use. In this case, 1.65 kilobytes. It'll tell you how big you can get up to. You can get up to 32 because that's the entirety of the memory on the Uno. Global variables tells you how much you have left, the maximum, and all that. So once we've done that, we've connected, and there's no debugging supported on the Uno 3 R3. Um, so let's upload. It compiles it, it uploads it, and the on the actual board, just take my word for it, it's on, and it is the built-in LED is lit. Now it blinked because I reset, and the send is just on, although that should have only been 1 second. But all right, let's see what we get. Serial monitor, which there we go. I don't even remember how to clear this out. Let's see. Yeah, clear output. All right. So yeah, we're getting an output there. Now let's get a little fancier here. Might as well work in using putty. So load up putty, and where do we want to connect? Well, we're not doing SSH, so we're going to do serial. We know that the port, I believe, is 3. Here's our baud rate. Let's just save the, actually, let's just say, I don't know, like we know serial monitor. I just realized I might have screwed up some of these other settings. Let me just make, no, I'm good. Okay. Okay, let's open it up, see what we get. Nope, that is the wrong thing. Weird, let's try that again. All right. Loading monitor, opening up. Oh, it's saying access is denied. Why? It's because we have this up. No, let's see if this, well, let's just verify the port though. Okay, yeah, it is COM3. All right, 9600. There we go. See, this is the old-fashioned way of bringing up a serial monitor. Actually, I think I just realized that you didn't see any of that, so let me do it again. Okay, so this is the actual thing. I keep forgetting I didn't change the window, but I've already set something up. It's set to serial. We know our COM port. We know our baud rate. So let's open her up. And here we go. We're getting this. We're getting the message that it's going over again. And congratulations! Just this basic serial connection gets you into a much wider world if you can do this in putty. All right, let's look around the rest of the IDE now. We have our opens, we have a sketchbook, we've got examples, all sorts of stuff here. These are official examples, and when you download custom libraries, a lot of the custom libraries will actually have examples for you for various things and should give you an idea how to use something. This is for rotary, some Wi-Fi stuff, keypad, various things. There's stuff with like the EEPROM, Ethernet, things you might be getting in a kit, SPI stuff, stepper, etc. Now the USB stuff's only going to work on like the Leonardo, anything that has native USB support, which the Uno does not. And there's even some basic stuff for the Arduino in-circuit serial programmer here. Moving across, you got preferences. You can set your sketchbook, location, font. If you have trouble reading this or you need something more, definitely don't feel like you have to stick with this. 14 is okay enough for me. When I was younger, 10 would have been fine. You got some themes here too. You've got high contrast, assuming that you have some moderate vision issue that isn't complete blindness. You got various languages, although you have to reload if you change that. You can verbose the output during compiling and uploading. You can set compiler, verify code after uploading too. So if you want to skip that step, I don't recommend it. You can also set for different places to look for packages and libraries. You probably shouldn't have to do this for like the basic Arduino Uno and a lot of basic sensors, but I use this for a lot of different boards. You got network stuff if you need to set that up. And then let's see, advanced keyboard shortcuts. If you need to figure out what they are. You can also edit them too. Let's see what else we got. We got cloud sketchbook so we can load up into the cloud if we want. Let's see. All the stuff under editing, decrease, increase font, find, replaces, copy, paste, everything. There's also auto format that'll kind of try to clean up your code for you in terms of the spacing and everything. Doesn't always like work like it should, especially more complicated sketches. And verify, compile, upload. You've got a couple of different options now. There's also options for using programmers and whatnot. We'll probably talk about that in a later video. We can include libraries. It'll just do it for us. We can add files as needed as well. Again, more complicated sketches that we'll get into eventually. Optimize for debugging. However, there's not a debugging option available to us. Um, there's still ways to debug, and again, I'll get into it in later videos. Archiving sketches, auto formatting, managing libraries, firmware updating. You can do that with the in-circuit serial programmer. You can also upload SSL root certificates. But yeah, you can see you can just pick the board, and I got a lot of stuff loaded up. But like, there's a long list of current uh, and past AVR boards built in here. Like, yeah, you got all sorts of some things I didn't even cover in pretty previous videos. And then you've got the keyboard. So you can use this to program the cube, but you're limited to what you can just do with the microcontroller. Anything past that, you'll have to use AppLab for. Or there's more convoluted ways to work with this. And then we can set serial port. This is just on what it detects. And as far as I know, there's no easy way to just set, okay, this device uses this COM port. It just assigns one randomly. Um, it and the way that virtual COM ports, because this is not the only thing that uses virtual COM ports, works on a computer. It could use 1, 5, 15, and then it just picks something random for the Arduino. I think COM port 1 and 2 may have special significance. I don't remember. You got stuff for the R4 boards. I've got stuff installed for all the AT Tinies. Um, Stuff for ESP. Basically just about any microcontroller dev board can use Arduino IDE. But keep in mind there may be features that this IDE doesn't support. So, like, you can only code in Arduino in this. You can't code in MicroPython, CircuitPython, etc. As I said, you can reload board data. That can be useful. Sometimes you can get board info. This may tell you something important, or it may not. I mean, this says serial number, PID, VID, and bin, what type, but this is really just all what the board says or what the libraries are configured. You can set up things to use like the Arduino as a programmer. You're really just attaching wires between things. There's instructions on how to do all of that. You can burn the bootloader as well. I think that still has to be done with the in-circuit stuff. But yeah, that's basically what it all looks like. I'll probably cover, I'll definitely cover Arduino App Lab when I make a video on the queue. Command line interpreter, I may eventually get into, especially when we start talking about Linux and single board computers. I've brought this up in many other videos, but Walkway is very good online simulator for the Arduino Uno Nano and Mega, among a number of other microcontroller development boards. Keep in mind it does have its limits. There's a lot of things it can't simulate, such as analog stuff. So current voltage, they can fake it, but that's only to a degree. It also has no idea, no way to determine if you've exceeded recommended operating conditions for components. So resistors are pretty much cosmetic, and it's not going to show you possible damage, such as burnt out LEDs. It can't function as a direct IDE, but you can copy and paste code between this and an IDE. It also doesn't require you to plug in the simulated USB, as there's no USB power, etc. So keep these things in mind. Does let you lay out some components, and you can also take a picture of that as a reference for real life. It's got a very active community that makes a lot of custom chips. Um, Support, though, for new basic components and things with the simulator would obviously have to come from the developer. We've also got another program called Fritzing. This is not free, but it's pretty inexpensive. It's a program that offers breadboard layout, schematic design, PCBs design. It does have an IDE environment that seems to act as a front end for Arduino One IDE. There's support for hundreds, thousands of different components, although keep in mind only a small fraction have SPICE simulator directives. So your options for actually properly simulating things are very limited. It's basically the de facto layout tool for when people want to show breadboard circuits. Mostly because at one point it was a free program, especially when it was still in beta. As I said, it's not free anymore, but it's pretty cheap. Worst come to worst, you can possibly find older free versions out there. And in this case, I'm not actually supporting software piracy because these versions were free at that point. Although the 2D nature of the program can make showing wiring and component placement a bit messy, it works on at least Windows 10 and up, Mac OS's, different versions for different versions of Mac OS. Linux, at least on 86 setups, as far as I can tell, there is no ARM support. It's got a very, very active community, and they're constantly making components, schematics, PCB layouts, and answering questions. Um, if you use the parts that have it, you can sort of use it as a spice simulator. Now, how exactly do you program this thing? Does it have its own programming language? Well, we usually call it Arduino, and it's a very simplified dialect of C++ that's designed to run on microcontrollers. that have as little as a few hundred bytes of RAM and a few kilobytes of flash. It can even run on something as small as that tiny 13A, which only has 1 kilobyte of flash and 64 bytes of RAM. But when you run it on this, you're running it with a very, very strict limitations. C uses a big int main as the entry point into the program. Arduino hides that in the background, and it has setup and loop. Setup is good is for doing things once, and loops it just keeps doing things over and over again. But on the back end, it's still doing the int main. It's just putting those two things inside of it, and you just don't see the bigger picture. The language itself can be described as compiled, statically typed, imperative, and procedural. It basically inherits that from being C++. It can handle objects, inheritance, polymorphism, encapsulation. It works with variables, arrays, pointers, structures, classes, templates. It can do function overloading, it can do virtual functions, and it handles dynamic memory allocation. There are a lot of things it's not, though. So we have a thing known as GPO pins. It stands for general purpose input output. Basically, individual pins on the microcontroller that have been routed or broken out so that users can use them more easily. The Atmega 328P, it has 23 pins that can be broken out by a dev board, such as PD 0 to 7. Um, PB 0 to 5 being broken out into digital pins 0 through 13. PB 6 and 7, they're used for the clock, so they can't be broken out. PC 6 is used for the reset button, so it can't be broken out. So we have 20 pins that are broken out into the Uno Rev 3. Of that, the Rev 3 has 14 digital pins. 11 of them have secondary functions. Some of them even have tertiary functions. You've got 6 analog pins that can input output analog voltages. And then A033 can also double up as digital pins. There's an in-circuit serial programmer header that's 6 pins. That's on the right from the pictures. It can be used to program the microcontroller directly and bypass the USB, but that's a pretty advanced feature, but you may run into that. The most frequent use is if, say, the USB or the serial over USB stops working. This can be a way to still use the board. At least with Arduino, a GPO pin, it can be set as input output or input pull up. This provides for an internal pull up resistor of 20 to 50 kilo ohms. Um, I'll be going over how to use that in future videos. Digital pins or any pins being used to digital, they have to be set with pin mode first. So as an input, output, or input pull up before they can actually be used for reading and writing. The analog pins work a little bit differently. They use a direct analog read, analog write. This also with pins that are pulse width modulation, you can essentially use both sets with them. It sort of does a, well, yeah, basically a fake analog. Although the analog is even fake too, because we're still dealing with digital. We'll be covering the secondary and tertiary pin functions probably in later videos. Now, here's the bare bones template for something that works in Arduino. You'll see void setup, um, and brackets and then curly brackets. The curly brackets basically encapsulate something so you know where it begins and ends. Void means it doesn't return anything. And in fact, I think with Arduino, these always have to be void. Um, Maybe there's some way to do exit codes, but nothing I know about. Setup, everything you put in setup, it does it once. Everything you put in loop, it just keeps going repeatedly. So yeah, pretty simple here. And then usually the first program people run is to blink the built-in LED. You'll see in setup, we do the pin mode. We use capital LED underscore built-in. This is a constant. With Uno, it'll always refer to pin 13. And then we're setting the output because we're sending a signal out from the board. And then in a loop, we're doing digital write, LED built-in high. Okay, turns it on. Or more properly, it's sending out basically 5 volts. Um, keep Yeah, delay 1000. In this case, delay uses milliseconds, so 1000 milliseconds equal a minute. Or sorry, a second, and then we do a digital write low. We basically turn it off, 0 volts, and we do another delay. So it's going to turn it on, wait a second, turn it off, wait a second, and just keep doing this. Now, the LED is built in, but it's also going to be sending the signal over pin 13. So it's really easy to switch that out. Now, I already explained how what a constant is. It's just something that's never going to change during the program. The compiler will automatically see that and will switch it to digital 13 in the machine code. So again, you'll see that built-in LED and any LED connected to digital 13 blinking. Now, keep in mind sometimes that internal LED is used by the Arduino for some other functions, like it'll do a rapid blink when the board has been reset. You can add multiple resistors and LED to 13, but honestly, I wouldn't do more than one because there is a hard limit of about 20 milliamps from any one pin, 200 from all the pins in total. You might even want to go lower than that, but that's basically enough for one LED on each digital pin. You can change the LED out for something else because you're just doing a high to low signal like a piezo buzzard, but keep in mind you still need a resistor to control the current peaks and the volume of the buzzard. Delay functions is measured in milliseconds, so 1000 is 1 second, but it might need to be absolutely precise. So if you need something with really precise timing, there's more advanced features to use. Um, the use of the delay one with the blink, you're basically going to create a pretty precise square wave, and you can measure that on an oscilloscope. And then we're moving here to something simple. We're going to do an input with the digital pen, with a digital pen. We're going to do a serial read. So we set it up. Now you'll see the serial dot begin 9600. We're establishing the baud rate. The COM port's already been established. Once this program runs and keeps on running, this is where you can use something like with PuTTY, and you just have to say the COM port, and then here's the baud rate. We're setting the pin mode, the push button to input because we're looking to bring in a signal. And then basically it will set a buttons. We're doing an int variable integer, and it's pretty much just going to be a 0 or a 1. Um, Digital read, push button, it's just going to keep checking. And then it's going to print out the button state, which is going to be, again, a 0 or 1. We're just laying for a millisecond so that we don't overload the system. Like, how often do we actually got to check? You can also bring that delay up to maybe as high as 40. I mean, you could be spamming the button, and it still takes you a certain amount of time to push it. So as I mentioned, we got some new code here. We've got serial begin that sets up the serial connection. It's establish a baud rate. For something like this, you can just set to 9600. That should be plenty of baud rate. The pin mode that sets a digital pin to input or output or input pull up. Um, Mind you, digital pin can only read a low or a high. A low is 0, a high is 5. The int name, you're defining a variable and it's statically assigned, so you actually have to tell it what kind of variable, an integer. So basically, you can define a 16-bit integer value, 2 bytes, and this can take a number from anywhere from negative 32,767 to positive 32,767. Um, it'll use 16 bits regardless of the sign or the actual number. So, if you just put in a 1, it's still going to use 2 bytes. Serial print, it writes something to the serial monitor while print line does this and adds a new line. You can have it read a literal signal, um, a little string with quotations or data in a variable without quotations. Um, this whole dot system where we see serial.print, that's object-oriented programming, at least to a limited function. The loop will just keep reading the state of that button, as I said, forever, and it'll be forever outputting the value until you pull the power. The delay lets the program kind of rest over so briefly, just make it at least a millisecond. just to give it a little reprieve. We also have a problem of switch bouncing. We're going to get more into that in a later video. Um, we can set a higher delay. This is a very basic way to do switch bouncing. So setting it to like 40 milliseconds will probably help because it's only going to check every 40 milliseconds. And let's get into using the analog pins. We're doing an input read and a serial write. So we're setting up our serial monitor on the top. And in here, we're doing an int with this sensor value, but we're doing an analog read at this time. And it'll print out the value you read. Um, and then we're just delaying 1 millisecond for the purposes of stability. Now, this introduces the analog read. It only works with the analog pins or digital pins with pulse width modulation, which is 3, 5, 6, 9, 10, and 11. And it basically reads a value between 0 and 1023 because it's a 10-bit analog to digital converter. The 10-bit sampling value in itself doesn't really correspond to anything specific. It just puts each aspect of the signal into one of those 1024 discrete values. You would have to put some logic into the program to actually give you the proper numbers or close to them. Potentiometer, that's actually what we're reading in that code, is a variable resistor, and how much is resisting is just translated from 0 to 1023. But you can kind of assume 0 means 0 ohms and 1023 means whatever max value of ohms possible with the potentiometer. This is a pretty good starting example for using the serial plotter as well, because you'll see a representation of the changes of the value being written to the monitor. In this example, we're kind of combining two of our early sketches. We're not going to be using the built-in, so we actually got to specify the pin. We're just saying LED equal 9. We are looking to do a brightness. We're going to be doing a fade. We're going to set it to 0, and we're going to decide that each level of the fade is 5. We're setting up the output pin, and we don't have to set up a pen mode for the analog one. So with analog write, we'll be setting the brightness to whatever, LED pin and the brightness. That's why we put the variable at the top. Say we want to change from like 9 to 11, 10. We can do that easily at the top of the program. Um, and then we'll keep going through this loop where we set the brightness by the fade amount. Um, and then we're going to sort of reverse the direction of the fading. Um, so basically, if the brightness is greater than a certain number or equal to it, and also less or equal to 0, we'll just be negating the fade there. And we're waiting 30 milliseconds just so we can see the dimming effect and provide a little bit of sanity to the microcontroller. Now, we've used the analog write. We can write a value between 0 and 1023 on any analog or digital write pin that has pulse width modulation. The delay provides for an actual public fading effect. Um, where 0 is the lowest brightness or basically off, 1023 is the fullest brightness, or at least through the resistor where we put down in the circuit, and the pin outputting the 5 volts, because we're putting LED out on the board. And at 5 volts and 20 milliamps, it's probably going to fry. Although I believe there may be some resistors built into the pins, or at least some of them. In case you make that mistake, keep in mind the analog write. That's not a true analog value. We're not saying 1 volt or 1.3 volts. Um, so you can't really use it to define analog voltages or output any voltages less than 5 volts. But it's doing some tricks there with the ADC conversion. Now, here we're looking at walk-we with an Arduino Uno here on the right, where again, we're not worrying about the connections, and there's some other stuff that doesn't work, like the A-ref or the IO-ref doesn't do anything, the 3.3 doesn't do anything. So let's dive in here with our Blink program. So let's do pen mode, and we're going to do LED built in. Notice how walk-we helps us with auto completion and suggestions. Do as an output. Okay, there's our first thing. Let's see how that runs. Okay, doesn't do anything, but yeah, we've set the port. So let's do a digital write LED built in. I set it to high. Let's see how this works. Okay, turned on the light. Um, so what happens if we do digital write LED built in low? Doesn't look like it's doing anything because it's going high, low as fast as it can. All right, well, we need to throw in a delay. So 1,000 milliseconds. Let's see what that does. Okay, it still doesn't do anything, even though we put in a delay. Well, we're delaying high to low, but we're not delaying low to high. So let's do that another delay. See what happens. Yep, see, we got a blinking light. And the same thing would work on Walkly. All right, let's see what happens when we add some components here. Well, since we're trying to simulate real life, we'll grab a resistor, grab an LED. Actually, let's flip around the LED. So we will connect the resistor to 13. I'm ignoring a breadboard, which I would normally use, although it's not strictly necessary. Actually, you know what? Let me do switch that over. This is going to be annoying. You know what? I'll just make this vertical. So over again. Then we also got it set up ground, if you remember, with a circuit. All right, let's see what happens. Oh, you'll notice, see, this external LED, because the built-in one is connected to 13. All right, now let's take a look at the second sketch, and that was we're doing a push button. So at the top, we're declaring an integer variable for which pin we're connected to. I've decided to pick 2. We're setting the input instead of output. We're going to a loop, we're setting an integer, and we're saying the button state will be digital read from that push button. Now I could have declared the int initially up here at button state and just set it here. But for our purposes right now, it's set the way it is. I'm also using a thing called camel case that's against convention of this programming language, but just ignore that for now. And again, the fact that I'm not declaring int button up at the top is empty and then filling it down here, that's also against convention. And we'll be using the serial monitor in this case. So we're beginning, and we're doing a print line with the button state. So we'll just see zeros and ones, and we're doing a delay of 1 millisecond. Okay, so it's just going to keep pushing zeros. Now the button itself, we have set up with the lower left is connected to the pin. The upper left is connected to a power source. Since we don't simulate analog, this is just a placeholder. And then the lower right, we're connecting through a resistor, which again is just cosmetic, but it's good practice in real life, to a ground. So basically, when the button's not pushed, the lower left is connected to the lower right. When we push the button, the lower left and the upper right are connected, and then the bottom right and the top right are connected. So we press the button, see, 1. Now it's checking this so often that this isn't telling us a single press, but it is telling us how we press. Well, what can we do here? Maybe let's see what happens. Let's do 40. We'll redo it. Okay, so effectively it's going to be the same thing. But yeah, you'll notice the button presses are only a couple of ones now instead of a full screen. Also, actually, you know, let's do some better convention. We'll declare it up there. That way we're only changing it. Doesn't really have an effect on the program. If we change the number up here, let's just say we'll put it 3. I'll put 4, whatever. All right, well, it's detecting 0 because there's nothing, it's floating. So, yeah, see, it's not doing anything. We would have to connect it to 4. So let's change it back to 2. Let's see, we've declared we're not going to change this. Then we got the button state. All right, so what could we do? We could do, let's see. Now change things up here a bit, add a little bit more functionality. So actually, let me clear out the serial monitor. Well, we've set up a last button state that we're going to compare to the first one. And so we're going to still stay with the button state here at the top. Um, but we're checking the last button state with the current one. If they're not equal, this is when we're going to print out. Otherwise, it's going to ignore this if it's the same. And then it's going to set last button state to button state and then 40 millisecond delay to help a little bit with bouncing. So yeah, see, 0, 1, 0, 1, it's reading it. We hold it down, it's not changing. So we've already seen how we can improve upon an existing sketch. All right, now we're setting up our analog read. We're keeping initially just going to kind of keep it simple. We're essentially going back to our push button, but we've connected it to A0 and we're doing an analog read. Note that we don't have to do a um, pin mode for this. So what should happen? It's just a push button on or off. It's off, it's a 0. If it's on, it's 1023. So two extreme values. Now I've replaced this with a potentiometer, but my code is still the same. So this will move us through values. So right now it's at 0. Whoops. Okay. If I move it all the way to the top, 1023. We start to move it down, it's going to go through those numbers. So that's how you do an analog read. Now, we can still improve upon this program, obviously. So we've set sensor value up here. We could set the analog pin up here too. That way, now in a simple program, this looks kind of pointless, but if you got a program where you're referencing the same thing over and over again, why keep making sure that it's a 0? Just set it up there so that you can easily change it throughout the entire thing. Okay, oops. All right, let's do this again. Same thing. Now we could also fix this. Let's do less sensor value, 0. Oops, less sensor value, 0 up here. We will now check if sensor value is not equal, not equal to less sensor value. Okay. Be printing out that message. So if the two are equal, it's just going to ignore it. So, but we also need to set the last sensor value. We're done here. We're going to keep it on this loop. See what happens. All right. So yeah, 0, 0, whatever. Okay. See, it's no longer just going through all the changes. All right, let's look at the next one where we're fading an LED. We used analog read before, but there's also analog write. We're going to set which LED here at the top, good practice. We're going to do a brightness. We're going to do a fade amount because it really depends how slowly or whatever we want to do this. We're setting the pin mode, output LED. It's on a digital pin, but you'll notice a little symbol next to it. That means it has pulse width modulation. So we can do analog read and write to it. So yeah, we start off with analog write. We're setting LED, we're setting the brightness. So it's going to start as off. One thing I should mention with this light in the simulator, it has some trouble simulating particular modes of light. You'll see it in real life, it would be much more full. So we're changing the brightness over time. Brightness equal brightness plus fade amount. Remember, our fade amount is 0, so it would be 0 plus 5 at first, so 5, 10, 15, 20, and so on, all the way up to 10 and actually no, all the way to 255. We're going to reverse the direction, and then basically if it's less than or equal to 0, or if it's greater equal to 255, we're going to basically negate it. So we're going to set the amount. So basically, once it gets to either less or equal to 0 or greater or equal to 255, um, then we're just going to switch the fade amount. We're going to make it negative so that basically it goes from one end to the other. We're going to set a 30 millisecond delay, and we're doing this because we need a delay to actually see the dimming effect. So yeah, let's take a look at what this looks like. It's going up, it's going down, it's going up, and it's going down. You can see the fade and dim effect in real life. This would be much more obvious. Now, if we connected this to say 8 or 7, it wouldn't work. We can only do analog pins, or we can do the pulse width modulation pins. I'll be getting into pulse width modulation in more in depth in a future video. All right, now I've brought things up in Simu IDE, which is another place you can simulate the Arduino. It's a little bit more involved than Walkly, but it does a lot more with analog simulation and such. So we got our little Blink program here. Now, there's some setup here for actually being able to compile and upload to the MCU here. Kind of annoying, but set the editor so the text is a little higher. There's doesn't seem to be any, well, there's a little bit of highlighting, but not what it is with the Arduino IDE. But that's probably not the point of this. So yeah, you have to set up compilers. You'll be wanting to use file. It's since it's Arduino, it wants a folder with a certain name, and then it wants an INO sketch file inside that with the exact same name. So if you make the sketch, you got to be mindful of how that all works. But we've set it up. We've got a blink going, and here it is. The two lights are blinking. I put a 1,000 ohm resistor here. Not really sure what happens if I took that down to nothing. Let's see. Let's see. One. Okay, so if it's going to be burning out, it's got this sort of square thing around it. Well, let's say 100. Okay, that's really bright, but it's not going to explode. 220. Still pretty bright. So I'm just going to set it to 1,000 because we can see it. That's the important thing. It's just an indicator. All right, here's fritzing, which I haven't shown too much yet. Um, Basically, this is just a setup for the blinking external LED. I've got wires running from ground to the cathode, and then we've got a resistor connected to the anode going to 13. I have it set to 470 in real life. This would be very bright, but it would be more than adequate. As I said, I think there might be some internal resistors protecting components to some extent on the Uno. I usually go with best practices anyway, so haven't really run into that. Now, there's no simulation for the Uno. There is for these other parts, I suppose. So if I hooked up power, the LED would light up. Here's an example with the digital pin push button. Nothing's really simulated here, but you can actually see proper wiring. I got a ground. We're using 13 in this case. We've got a resistor set to the button. This is basically, I didn't explain earlier, but this is basically to prevent random amounts of floating around voltage from accidentally triggering the pin, because that does happen. You want a solid amount of power that's going to be triggering the button. And then we've got our power routed all the way to 5 volts. So when the button's pressed, this is 13 is going to be input, and it's something going to get 5 volts. Otherwise, it's just connected to ground for a solid 0. Now, this would be a wiring setup for a small potentiometer. Yours actually might look differently, but the idea is the middle pin is used for the signal. I have it connected to the digital pin 6, but that pin has pulse width modulation. And then we've got power and ground on either side, and we would just be using this to input read an analog value. So let's just wrap things up. Well, the Arduino Uno R3 comes in the official models, unofficial ones, and compatible clones, although the functions should sort of all be the same. The compiler, you tell it the model you have, and it compiles the sketch for that model. Arduino programs are called sketches, and they're basically a form of C++, designed for small microcontrollers. It does procedural coding, but it does some object-oriented stuff as well. The IDE allows you to code, verify, compile, and upload that sketch to an Arduino through a serial to USB converter. As I said, the computer thinks it's talking to USB, the microcontroller thinks it's talking to serial. For serial communication, you always need to know at least the baud rate and the COM port so that it can be agreed upon for whatever is monitoring or plotting the serial, and basically for the sketch to be read correctly. You don't have to set those things up if you're not going to be using the monitor or the plotter, though. The Atmega 16U, at least on the official models, that's what converts serial to USB and back. As obviously most modern devices, especially PCs, don't have the serial ports anymore. Um, there is the end circuit programmer. That's an advanced feature, but it's a way to get around that. I talked about a couple of different sketches, a few different keywords and things with Arduino, set up a basic sketch, a couple of the functions. We also looked at that in Walkwe. Keep in mind, just keep experimenting, but keep in mind there are limitations to the serial versus the specs of real world equipment. Well, until next time, have a good one.